Now we're going to take the volume of a three-dimensional object that is being rotated around an axis of rotation. So if we think about like a rectangle that is being, it's basically the area between the distance between two curves, and we take that stick, oh, think about like a flag on a toothpick, and then you rotate the toothpick around, the flag will make a circle, right? Yeah. What we're going to end up doing is finding the area of the circle and then taking the integral to add up all the different areas of the circles. So what we can see here is this. We have the distance between two curves. I'm going to rotate it around this axis of rotation. And if I do this infinitely many times, okay, I end up with something that looks, well, this is bands. I end up with something that looks like this, right? Okay. And then if we take and cut the curve up into smaller chunks, so infinitely many um, rotations, then that is us taking the integral of the area of the circle, and then we end up with this three-dimensional object thing. So what you notice is that when you rotate around your initial radius, you end up with a circle, right? You end up with a circle. So the shape that we're adding up over the bounds is a bunch of different little circles, okay? So disk method. I think about this as perpendicular because the way I'm cutting up my curve is perpendicular to the axis of revolution. So I'm going to turn the toothpick. So if the revolution, I'm going to call my axis of revolution the toothpick. I'm going to cut the curve to the axis of revolution, well, perpendicular to the axis of revolution, so that when I turn the toothpick, it makes a circle, okay? So the distance between the curve to the axis of revolution is r. It's the radius of the circle, okay? My bounds will be however far I am making circles, so from A to B, and that's it, okay? And because my bounds are horizontal, I'm cutting up different radiuses in dx direction. If my axis of rotation is the y-axis or vertical, so this, now I'm taking a vertical toothpick and spinning it, I'm going to take a cut of between the curve to the axis of rotation, going perpendicular to that axis of rotation, and I'm going to spin around my curve to give me my r is the right curve minus the left curve, and my bounds are going to be from C to D. Okay, so go ahead and write in these equations. The volume is going to be, basically, we're adding up a bunch of circles. So it's pi r squared. But when I'm going to add up a lot of circles over time. So it's the integral from C to D times pi r squared. And then with a vertical axis of rotation or revolution, we use our equations in terms of y, okay? Because we're cutting our radius horizontally, okay? For a horizontal axis of revolution or rotation, we say the volume is equal to pi times the integral from A to B of r squared dx, okay? And in this case, it'd be like top curve minus bottom curve. So let's go ahead and play around with this a little bit. Find the volume of the solid formed by revolving the region bounded by the graph of f of x is equal to the square root of x, and the x-axis from 0 to pi, and we're going to rotate about the x-axis. Wow, that's jam-packed with information. All right, so we are going to start from 0 to pi, and the curve goes up to 1. So I know that the square root of sine looks like this. It's just like a little curve, okay? And our shape is bound between 0 to pi, the x-axis, and the curve, the square root of the sine of x. Okay, so I will be spinning the graph around the x-axis, which means that I need to create a flag perpendicular to the x-axis. And then so when I spin the flag around, it will make a circle. So the radius of the circle, depending on where I draw it, okay, will be the top curve minus the bottom curve. So the radius is going to equal the top curve, which is the square root of the sine of x, minus the bottom curve, which is 0. So we just get the radius is equal to the square root of the sine of x. Okay, so to find the volume, we say it's a lot of circles added up over time, so we're going to use the integral of pi r squared dx because we are cutting up xy's, okay? We're going to use the bounds from a to b. I can see that my left bound is 0, my right bound is pi, okay? My radius is defined by the square root of sine of x, and then remember you have to square that because you're actually finding the area of a circle, so squaring your radius, dx. So I get the volume is equal to pi times the square root of 0 to pi of sine x dx. And I went ahead and just used a calculator and got 2 pi. All right, so the volume of the shape formed by this curve being rotated around the x-axis would be 2 pi. All right, let's do the next one. All right, find the volume of the solid formed by revolving the region bounded by the graph of x squared plus 1 and the y-axis for 1 is less than or equal to y, which is less than or equal to 5, about the y-axis. That sounds like fun. Okay. So 1, 2, 3, 4, 5. That's where I'm going to start. Okay, so y is equal to x squared plus 1. So that has been shifted up 1. And then it's going to go like very, very steep. Okay, probably steeper than that. And then we end up with we want it bound by the y-axis, it says, and 1 to 5. So at y is equal to 1, the graph intersects with the y-axis, and then at 5, the graph is going to intersect with the curve. Okay, so we're going to take this yellow area, okay, and we are going to spin it around the y-axis. So now I'm going to have to create a flag going perpendicular with my axis of rotation, and it's going to spin around like so. So the radius is going to be the right curve minus the left curve. So the radius is equal to the right curve minus the left curve. And one thing I noticed is that this curve y is equal to x squared plus 1 is written in terms of x. We need to get it in terms of y. So I'm going to subtract 1. I get x squared is equal to y minus 1 square root. So I get x is equal to y. Well, x is equal to plus or minus the square root of y minus 1. And I also noticed that this is only the positive side, so it's going to be the square root of y, positive square root of y minus 1. All right, now to get the radius, now that I'm written in terms of y, the right curve is the square root of y minus 1. The left curve is 0. So the radius is equal to the square root of y minus 1. Now we can find the volume of our figure. So lots of circles added together. So it's pi times the square times the integral of the lower bound is y is equal to 1 to the upper bound y is equal to 5 times the radius squared. The square root of y minus 1 squared dy. So I can write it up here of r squared dy. Okay. So I end up with the volume is equal to pi times the integral from 1 to 5 of y minus 1 dy. I do need to evaluate this, but I'm going to use a calculator, and I get the volume is equal to 8 pi. Next, this time we're going to revolve around a line that is not the x or the y axis. If you draw it out, it makes a lot more sense. Okay, so find the volume of a solid formed by the revolving region bounded by f of x is equal to 2 minus x squared, and g of x is equal to 1, and we're going to revolve around the line y is equal to 1. Okay, so shift it up 2, and then it is a negative curve. Let me draw that. A negative parabola. So over 1, down 1. And y is equal to 1 is another place that we are bounded. And then we are also revolving around y is equal to 1. So I'm only spinning around this little hill right here, this little yellow hill. Okay, so when I spin this, I'm going to create a flag that is perpendicular to my axis of rotation. I'm going to spin around a little circle, something like that. So the radius is going to be equal to the top curve minus the bottom curve. So the radius is equal to the top curve, which is 2 minus x squared, minus the bottom curve, which is 1. Simplify that to give me 1 minus x squared. So now I can just figure out the volume is equal to pi times the integral from a to b of r squared dx. Okay, so the left bound would be -1. The right bound is 1. I know this because I've drawn a lot of parabolas before. If you need to set the two equations equal to each other, you can. Okay, so we can figure out the intersect by saying 2 minus x squared is equal to 1 and solving. So I get 0 is equal to x squared. Let's subtract 2 from both sides, minus 1. And then I actually am just going to factor this. So x minus 1 times x plus 1. So x, the intersections are going to be at 1 and -1. So you can always solve for the intersection if you want. Okay. All right. So anyway, going back, we have pi times the integral from -1 to 1, or x equals -1 to x equals 1 of the radius squared. And the radius is calculated by the equation 1 minus x squared. And then we're squaring it again because it's the whole radius. So I will plug this into my calculator, and I get the volume is equal to 16 over 15, or 1.066, or 1.067 if it's truncated, or if it's rounded, sorry. All right, a couple more. So find the volume of a solid formed by revolving the region bounded by y is equal to the square root of x plus 1, y is equal to 3, and x is equal to -1. And we're going to revolve about x is equal to -1. So we're drawing this again. I always draw them. All right, the -1 shifts us to the left 1. And so we're going to start right here. And then it's a square root function, so I go up 1 like that, and then 1, 2, 3, 4, up 2. Mother functions, you know. All right, and then we have the equation y is equal to 3. So 1, 2, 3. Looks like I'm going to have to extend out my curve. And then x is equal to -1. Okay, I'm going to extend out my curve. Whoa. Okay. And then we're going to revolve around the line y is equal to 1. So this guy right here. And it looks like the region bounded is the region right here above the curve. And then we're going to take since the line of rotation, the axis of rotation is vertical, I need to cut the area horizontally and then create a circle. Spin my toothpick around to create the circle so I can see the radius. This time the left, so it looks like the radius is equal to the left curve. And I look just to make sure that the one curve is always the left curve, just in case I have to make, or sorry, the right curve, just in case I need to make 2 integrals, okay, minus the left curve. So the radius is equal to, and again, I have a problem because my right curve, sorry, y is equal to the square root of x plus 1 is written in terms of x. So I need to get this in terms of y. So I get y squared is equal to x plus 1. So I get y squared minus 1 is equal to x. Yep, so our right curve is y squared minus 1 minus, and this time our left curve is x is equal to -1. So I'm going to subtract -1. So I get, when I simplify, I get y, the radius is equal to just the equation y squared. Now we can figure out our volume. The volume is equal to pi times the integral from c to d of r squared dy. So the volume is equal to pi times, the lower bound would be 0. The upper bound is y is equal to 3. It's kind of nice. We didn't have to figure out what this intersection was. I mean, you could, but you don't have to figure out what the x value of the intersection is. So from 0 to 3 of the radius, which is y squared, dy. So the volume, using a calculator, is 48.6 times pi. All right, last one. So find the volume of a solid formed by revolving the region bounded by y is equal to x squared, the x-axis, and x is equal to 2, about the line x is equal to 2. All righty. I don't know why I drew it like that. That was weird. Okay. 0, 1, 4. Okay, and then so I get y is equal to x squared, the x-axis, that would be right here. X is equal to 2, which is right here. And then we're going to revolve around x is equal to 2. So I'm looking at this yellow region. Our line of rotation is vertical, so I need to draw a horizontal radius. I would like to draw in a little circle to help me see the rotation that's happening. Okay, so the radius is going to be equal to the right curve. Because it's horizontal, it's right minus left. All right, so this time we have, oh, there's one more after this, sorry. This time the right curve is x is equal to 2 minus the left curve, which is y is equal to x squared. Let's write that in terms of y, so the square root of y plus or minus, and it's only the positive side, so it's only going to be positive y, the positive square root y. So it's 2 minus the square root of y gives us our radius. Our bounds are from 0. Let's grab another color. From 0 to where the x equals 2 intersects our parabola. So we can figure out the bounds by saying when y equals x squared, when x is equal to 2. So when y is going to equal 4. I'm basically substituting in 2 for x to just solve for the y value. Okay. So lastly, let's go ahead and set up our integral. We have the volume is going to equal to pi r squared, the integral of pi r squared. So from the integral from c to d of pi r squared dy, because we cut the curve up vertically into we're stacking circles up vertically. Okay, so I'm going to have the bounds from 0 to 4. My radius is dictated by the equation 2 minus the square root of y squared dy. And we get a calculator out, my handy dandy calculator, and get 2.667. All right, real last one. So find the volume of the solid formed by the revolving region bounded by y is equal to x squared, y is equal to 4, and the y-axis about the line y is equal to 4. Okay, so this one's really similar, but it has a little bit different stuff going on. 1, 2, 3, 4. 1, 2, 3. Okay, so x squared would be 0, 0, 1, 1, 2, 4. Graph that in. Y is equal to 4 is up here. The y-axis is right here. And then we're going to revolve around the line y is equal to 4. So this also is my line of rotation. So I'm going to take this yellow area, and the line of rotation is my toothpick. So I'm going to take this right here. I have to cut perpendicular to my line of rotation, and I'm going to end up with a circle like that. Okay, so the radius is equal to the top curve minus the bottom. And this time the top curve is the line of rotation, so that would be 4. And the bottom curve is the parabola, so minus x squared. So the volume is equal to pi times the integral from a to b of r squared dx, because we're stacking up circles horizontally. Okay, so think about like a Hasselback potato, stacking the circles horizontally. That's dx. Okay, so we have the integral from 0 to 2, because that's where the curve intersects the line y is equal to 4. 0 to 2 of 4 minus x squared. Oops, I forgot a squared. 4 minus x squared, all of that squared, dx. And when I plug that in, I get the volume is equal to 17.06 or 17.067 or 17.06 bar times pi. Whew, almost forgot my pi. Okay, and that's it for today. I have 2 more volume methods, and then we're almost done with this chapter. All right. Have a good one.